name is Elmo Alexander. I was an AP/AB Calculus student during the 2015-2016 school year.
And I'm Bryce Rosenberg. I was also an AP/AB Calculus student from the 2015-2016 school year.
Today we're going to be solving the 2015 AP Calculus for response question 2. Feel free to pause this video at each part of the questions to familiarize yourself with what it's asking. Now, part A asks us to find the sum of the areas between regions R and regions S of the given graph.
So first things first, how can we find the area between these two sections? Well, we know that to find the sum of the areas of region R and S on the graph, we have to use an integral in the two given equations from the problem. When we set up an integral, that tells us the area from that curve to the x-axis. So it's this region right here. It's not just R, it's all the way down to the x-axis. Remember that area is a two-dimensional function, and when we multiply the distance from the x-axis of the equation by our dx, which represents the width of a rectangle, this adds a second dimension to give us area. Setting up an integral gives us the area of that curve to the x-axis. So let us color code what area we would be finding if we were to set up an integral with each equation. So, to find the area between two curves, we have to think about this. Big minus small equals the area in between. So knowing this, we can either set up one integral with the larger function subtracted by the smaller function, or we can set up two integrals, the first one being the larger function and subtracting that by the second, smaller function. I think the easier method is to write out one integral per section. So let's go with that.
So this would represent just one section of how we would set up this integral. So what is a larger integral, you ask? Well, it's actually pretty simple. If you look at the graph to see which function has greater y values, so this one has the greater y values, we can tell that in this section right here, this is the greater function. Now, if you look at the graph, we can see that a problem occurs at this point A right here. We can see that there is a point where the functions switch, which is greater, so we know that we're going to have two different sections, that's what we're going to call them, where we have two separate integrals, one here and one here. One section for part R, obviously, and then the other would be for part S. And we have to add the total area for each section to find the sum, which is what the question is asking for. So, how can we figure out the point where the functions equal each other? So we can set up the integral with its bounds correctly? Well, this is where our calculator comes in handy. The easiest way, in my opinion, to find the intersection point is to plug in the functions into the calculator and make the calculator find the exact x value of the intersection. So what we do is we type our equations into the calculator, as I've already done here, and then we go to Second Calc. Scroll to number 5 where it says intersect. It's kind of hard to see on the screen here, but number 5 on your calculator should say intersect. Select a point near the intersection on both functions depending on what type of calculator you'll have. This might be a little bit different, but it's not very good on the screen. But you have two curves there that model the graph. Sorry it's so bad. But you have this curve, so we're going to hit enter. And we're going to select our second curve, which the calculator should be doing automatically here. And then we're going to select a point closest to the intersect, so just a guess it's going to ask for. And then it tells us our intersection. Now that we know the point at which the two integrals switch from greater to lower and vice versa, we can write out the integrals whichever way we want, as done in this part right here. So we can set up our integrals according to this, so the greater function minus the lesser function. So we'll go ahead and write out the integrals. So we have one integral here from 0 to point A of our greater function, which in this case is x to the 4th minus 6.5 x squared plus 6x plus 2 minus our other lesser equation, which would be 1 plus x plus e to the x squared minus 2x dx. So this is our integral for section R. So we'll go ahead and label that as R. We can plug that into the calculator now. So we would go to math, number 9. Again, it's hard to see. So we have our point here, 0 to A. What was our point for A?
1.032.
So I probably should have written that down. So A equals 1.032. All right. So back to this. So for our integral is from 0 to 1.032 of our first equation, which is going to be, like I wrote down a second ago, x to the 4th minus 6.5x squared plus 6x plus 2, close parentheses, minus, open parentheses, 1 plus x plus e to the x squared minus 2x, close parentheses. And then obviously we have to put our dx in there. And there's our area for section R. Now we have to do that again for section S. So our integral goes from point A to 2, I believe.
Yes.
And then, again, since our function switched, which one's greater, we now have to subtract the opposite one. So this was the lower function in the first part, this curve right here, but now it's the greater function. So we do big minus small again. So we have to start with this equation because that's the curve that's now bigger. So we do 1 plus x plus e to the x squared minus 2x minus opposite again because this is a lesser function, x to the 4th minus 6.5x squared plus 6x plus 2 dx. So then our area for section S would equal, as Bryce is about to plug in for us, so we have 1.0069, and then we add our two sections together, and that brings us to our answer of 2.00434. And that's our answer for part A.
Now you know how to find the area of two regions of a graph, so let's move on to part B. This part is asking us to find the volume of the solid created in region S. How do we find the volume of a 2D graph and what does it look like? Well, let's start by using a 3D model. We have created a model by cutting out different sizes of squares from foam paper and lining them up perpendicular to the x-axis. Before we show you that, think about this. If we know that dx represents width, what will the value of the height and length be represented by? By cutting out squares, we are given a basis for the dimensions and equations needed to find the volume of the created solid. This is a rough visual representation of what it would look like if we were to make squares from the cross-sectional area. So from the problem, it wants to know the volume if the cross-sections are squares. So from this, we know that whatever the distance from the curve, which we can call length, the height will be the same, as you can see here in the representation. So now we have our length and height, which are the same value, and our dx, which represents the width. How can we be certain that we are finding volume with our integral? Since volume equals length times width times height, and the L and H are the same, we can simply square the part of the integral that represents length and height, and then add our dx, which represents width. Now we get to the idea of finding the volume of the created solid. To begin, we have to bring back our integral for region S.
So we know that dx represents the width of the integral. But don't forget that we have to use that we've used squares to create the volume of the region. So with that being said, if we know that dx represents width, what will the value of the height and length be represented by? Well, as we've just said, each side of a square is equal, so the height is equal to the length. Now, we need to set up an integral in order to solve for the volume of the region. So to begin, the equation for the area of region S will be used in this integral as well, but this time there's going to be a twist. The entirety of the integral needs to be in parentheses, and it will be squared with a dx after the parentheses. But again, we have two ways we can write out. We can write out our integral, as you might recall from part A, but we're going to go with writing it as 1. So that's one method, but I prefer the other one where we write it as 1 integral, so f1 of x minus f2 of x dx. That's the method I prefer. So remember that we have to square our length because it represents both length and height. So right here, this represents our length because it's giving us the area in between the two graphs. Right here, this is our length, and we square it because our height, which is represented in the vertical right here, so this is our length and this is our height. We have to square that because those are the same. And then our dx comes into play right here where we multiply by the width. So we have 3 dimensions.
So we also need to make sure that the correct limits for the integral are used. The same limits as were used in finding the area are used in finding the volume of region S. So the lower limit will be 1.0328 and the upper limit will be 2. And the volume of the equation is approximately 1.2832. Now we have found the volume in region S, so let's move on to part C. Part C is asking us to find the rate at which h, in terms of dh over dx, changes with respect to x when x equals 1.8. Remember that a related rate is, in essence, a rate of change. What else do we know that is called a rate of change? A derivative. So we are going to have to set up an equation that is given to us and take its derivative.
So we know that h is the distance between the two graphs in section S. So how can we find the height, or the distance, between the two functions? Well, if we think back to part A, where we found the area of each section, we had to use this idea of big minus small equals the distance between in order to figure out the area of each section. We're going to use a similar principle here. So we're going to color code this, and this is the area under each curve, and this is the area in between, but we're only dealing with section S. So we are going to subtract our big equation, which is 1 plus x plus e to the x squared minus 2x, which is this, so this big curve, by our little equation, which is x to the fourth minus 6.5x squared plus 6x plus 2. So this equation right here.
So we have a base equation of h equals 1 plus x plus e to the x squared minus 2x, parentheses, minus, parentheses, x to the fourth minus 6.5x squared plus 6x plus 2, close parentheses, which tells us the distance between the graphs in section S at any value of x from point A to 2. Now, if we plug in this equation into our calculator, we can see what h is graphically. Now this represents the length of h at any given point along our interval, which is a until 2. But what we want to know is the rate of change, or slope of h at x equals 1.8. So the easy way to do this is to graph our equation and let the calculator take the derivative, or rate of change of h, at x equals 1.8. So plug in the equation into your calculator. Sorry.
You're good. You're good.
Okay. So plug in the equation into your calculator. Go to Second Calc, scroll down to number 6, dy over dx, and type in your x value of 1.8. So the calculator will do it all for us, and it gives us our answer of negative 3.812. But just so we make sure you know why you're doing that, let's go over the problem on paper and save the calculator for later.
But like we did earlier, we need to take the derivative in order to find the rate of change of the value of h, or our dh dx. So we need to take the derivative to give us dh dx, but we'd also have to take the derivative of the other side of the equation. But this time, like I said, we're going to write dh dx after we take the derivative. So then we have write out the equation, and then there's our derivative. Just to save time, I didn't write that all out. Now that we have the derivative, all we have left to do is plug in our points. The question asks for the rate of change of h at x equals 1.8, so we have everything that we need. So let's store 1.8 in our calculator as x. Can you read that?
Yep. So to do this, you press 2, then STO, then X.
Say correction 1.8.
Correction, 1.8. So now we can put in our equation for the rate of change. Then all we have to do is press enter, and there's our answer. Same as what we got when we plugged the answer into the calculator.